Hi, I'm Iyad. A friend of mine sent me this pyramid asking me to prove it's true. One might say, don't you have a calculator? Of course, one can simply verify it's true using a calculator, but what he meant was proving it using pure mathematics. As you see, there is a nice pattern there, and it's a good exercise on the use of mathematical series. It might also be interesting to those who just like to practice some mathematics as a hobby to refresh their sense of logic and intuition. Well, let's prove it using arithmetic, just to catch the idea of the proof, and then we move to the abstract one. And let's take any of the 10 equations here, such as this one. We notice that these two numbers complement each other. To explain what I mean, let's put them vertically under each other. We can see that each digit of this number complements its matching one from the other to 10, which inspired me to add this number to both sides of the equation. On the left-hand side, we already have 8 of this number and we added one more, so we will get 9 ones. 9 times 1, 2, 3, 4 plus 4. While here we will get this. We've got 4 ones and 1 0 because we started from a 4-digit long number. So for this equation to be true, we just need to prove that this is equal to this. We have 9 times this number, which is 10 times this number minus 1 of it. We write the left-hand side, so it's, and this is, if we add this, it will become 1, 2, 3, 4, 4, minus 1, 2, 3, 4, which is clearly 0. 4 minus 3 is 1, 3 minus 2 is 1, 2 minus 1 is 1, 1 minus 0 is 1. And it's done. So this equation is correct, which means that this equation is also correct. And the same method can be applied on any of these 10 equations. And now let's move to the abstract proof. We notice that we have a couple of forms of numbers. The first form that we see on the left-hand side is formed of digits that are increasing. And as they are increasing, so I call this form In. For example, we have I4 is 1, 2, 3, 4. It consists of digits from 1 to 4, which is n. So it's the decimal number 1 to n. While on the other hand side, we have kind of opposite form. It consists of digits that are decreasing. For example, we have D4 is 9876. It starts at 9, which is 10 minus 1, and it ends at 6, which is actually 10 minus 4, which is n, which is why I wrote it like this. And thanks to this notation, we can abbreviate the whole set of 10 equations here into one equation like this. We have In times 8 plus n equals dn. And the next step is to write each of these two numbers in terms of n. For example, let's take I4, which is 1, 2, 3, 4, is equal to, which can be written as a sum from k equals 1 to n of k times 10 raised to the power of n minus k, because here we have 3, 2, 1, 0, with n equals 4 in this case. Similarly, we can write dn as the sum from k equals 1 to n of 10 minus k times 10 raised to the power of n minus k. So let's sum it up. And now let's try to use the same approach that we used in the arithmetical method. That is, let's add in to both sides. So this equation becomes, the task now is to prove that this equation is correct. And here, let me call what we found in the arithmetical solution. Then we found this number. And of course, this was for the case n equals 4. Well, this number is so special. Actually, it can be written as which is equal to which is the sum of the exponentials of 10. So it's the sum from k equals 0 to 4 of 10 raised to the power of k, which means that we are seeking to reach this formula from each of the two sides of the equation. So this is the right side. Let's simply substitute the value of each of these two numbers. This is equal to the sum of this sigma and this sigma. And as the boundaries or the limits of the sigma are identical to each other, we can unify them in one sigma. And we notice that we have this exponential of 10 is a common factor, so it becomes, and here we notice that we have positive k and negative k which cancel each other. So this is, and here the power of 10 is 1, so it adds to this power, it becomes. And now we're going to use the method of changing the variable. Let's take all this term and call it I. And to know how this change in variable will affect the boundaries of the sigma, let's make this simple table here. When k is 1, I will be n minus 1 plus 1, which is n. And when k reaches n, I will be n minus n plus 1, which is 1. So here k equals 1 matches I equals n, and k equals n matches I equals 1. And as addition is commutative, so it doesn't matter if we start adding the nth term backward until we reach the first term, or vice versa from the first term till we reach n. It's just the same. So we can write, and it remains for you to know that this variable actually is just kind of a placeholder. You can put here instead of I, k, j, or any other letter, it doesn't matter. So this is exactly sigma, and this is the formula that we've been seeking. As for the left-hand side, also here, let's recall what we did in the arithmetical solution. We worked with the case of n equals 4, and this is I4, and we wrote it as 10I4 minus I4 plus 4, which is equal to this number minus this number. But what we didn't mention then is that this number is actually I5 minus 1, because I5 is 1, 2, 3, 4, 5. I5 minus I4 minus 1. Let's follow the same approach with this term here. So this is 10In minus In plus n. And let's just substitute this value from here. And we can insert this 10 inside sigma, so it adds to the power of this 10 inside. So it becomes, and let's remember that we're trying to make the term in plus 1 appear here in the equation. Let's first write what is in plus 1. This is in plus 1, and it's derived from the same formula of in, simply by replacing each n with n plus 1. Unfortunately, we already have plus 1 here, so n plus 1 is ready, but the term n plus 1 is missing, and we can manage to solve this by adding the last term n plus 1 to sigma and then subtracting it from the equation. So we write this is the sigma from k equals 1 to n plus 1, and now we have to subtract the term n plus 1 from the equation. What is the term n plus 1? It's simply obtained by substituting each k with n plus 1. So it's times 10 raised to the power of n minus, we have here k, it is n plus 1 plus 1. They cancel each other, so this power is 0. The whole thing here is 0. And as you know, 10 raised to the power of 0 is 1. So all this term is times 1. Thus, this is equal to, or in plus 1 minus in, and here we cancel n with n, and we have minus 1. Let's substitute each of them with its formula here. This is in plus 1, and this is in, and not to forget minus 1. And now let's try to unify these powers here and here. And this is done again by changing the variable. But here no need to write a table, we can do it right away here we need to start from 0. So we need to decrement k with 1. So it becomes from k equals 0 to n. But to make the balance inside sigma, k has to be incremented by 1. So instead of k, we write k plus 1. And if you're still unsure of this, just try to substitute k equals 0 here. You will see that 0 plus 1 is 1. And here, for k equals 1, the first term is also 1. So this is correct. Times 10 raised to the power of, we have here n plus 1 minus k plus 1. And we notice that here plus 1 minus 1, they cancel each other. So we can write it n minus k. Then we continue. Now let's try to unify these two sigmas in one. We notice that they have similar boundaries except that this has one more, which is the term 0. So let's neutralize the term 0 alone. For k equals 0, we will have here 1 times 10 raised to the power of n minus 0. So it's 10 raised to the power of n plus sigma. So actually, those two terms are equal to this one. And now we can write those two sigmas together. And we can take 10 raised to the power of n minus k as a common factor. And positive 1 and negative 1 are cancelled with. So it becomes, we've got here. And finally, we need to prove that this is equal to this sigma. But we notice this difference, that this 10 has power of k, while here is n minus k. So you say it, we should make a change in variable from n minus k into k. Let's define I equals n minus k. And we will have, here is I and here is k. And when k is 1, I will be n minus 1. While when k is n, I will be n minus n, which is 0. Which means that the terms here will be from n minus 1 to 0. Therefore, this is equal to, and we're just 2 steps away from this. Actually, here we have one term that is here present but is not present here, which is the term 0. And what's the value of this term? When I equals 0, we notice that we will have 10 raised to the power of 0, which is 1. On the other hand, here the term n is missing. But fortunately, here is the term n, because for I equals n, we will have 10 raised to the power of n. So that's it. Actually, this is equal to the sigma from I or k, it doesn't matter, as we agreed, 1 to n, 10 raised to the power of k. So here we have, this is also equal to this sigma. Thus, those two are equal to each other, and therefore this equation is correct. I hope this video was useful and interesting. You may support my channel by subscribing and liking the video, and thank you.